Hello, everyone. I'm Andrew Calway from the University of Bristol. I'm chairing the Virtual Futures track. Those of you who weren't here this morning, this is a track that's been sponsored by the two universities, UE and the University of Bristol, and we brought over 4 keynote speakers to tell you about their views on the future of VR. So it's my pleasure to introduce speaker number 3, who is Hrvoje Benko, who's a senior researcher at Microsoft Research based in Seattle. So Benko, as he prefers to be known, which is good given his first name. So I would describe Benko as a serial innovator in AR and VR in the research community. So he does exciting stuff. Those of you not familiar with academic conferences and things, he presents at the major conferences on HCI, for example. He's a regular presenter at CHI, and has won Best Paper Award several times, as I remember. Yep. So this is a real pleasure for us to invite him here, and thank you very much for coming over the pond. So it's much appreciated. And he's going to tell us a little bit about his ideas of the relationship between perception and reality. So over to you, Benko. Thank you very much.
Thank you so much. Thanks for the introduction. I just want to say a few things about myself. I work for Microsoft. I work also for Microsoft Research. I'm basically an academic kind of scientist for Microsoft. So while I consult on products, I definitely help the HoloLens team and things like that. Today, I will not be talking about HoloLens per se. My charter, as everybody in Microsoft Research, is kind of chartered to basically invent the future and kind of think ahead. So I've been doing augmented and virtual reality interfaces for about 15 years now. And I have a slightly different perspective on some of the important things in there. So hopefully I'm trying to inspire you to think about designing these interfaces in a slightly different way. That said, I think we can all agree that in AR and in VR, we are really obsessed with creating this rich sense of reality. As a matter of fact, reality is 50% of the term AR and 50% of the term VR, also MR. Doesn't matter. This indexing on reality kind of permeates everything that we do in there. Oculus would like to think that this is the living room that you get. You put your headset on. HoloLens and Microsoft would like to reimagine how you do work and how much augmentation can you do that and make it seamlessly integrated into the environment. There's projects that try to do that for teleportation, holoportation, trying to get you to remotely collaborate on the distance. And all of these and many, many more, people really index on creating this rich sense of reality. But I will postulate a question to you is chasing reality really the best strategy for creating some of these interfaces? And since I'm posing this in kind of slide 3 or 4, my take is, and I hope to convince you that I think probably not. I go back to the words of my dear colleague, Mark Bolas. He used to be a professor at USC. Now he's at Microsoft. He mentioned a couple years ago that the world is a framed and malleable construct that the user creates in their mind. To me, what this really means is what is real and what we perceive as real is not necessarily the same. And I think as we create these interfaces, we should really exploit the fact that the real and perceived as real is not the same. Perceptual psychology has these illusions that are kind of canonical illusions that you guys must have heard before or seen before that illustrate this on a kind of a 2D way. This is, a typical one, like a faces or a vase. Depending on how you look at this image, you can see different things. Or do you see a young lady or an old lady? Matter of perception, matter of how you look at the picture. Or some of the more interesting ones are these lines straight or crooked? Now, if you took a ruler, of course they're straight, but do they look straight to you or do they look crooked to you? Or is this image moving or static? Now, I don't want to say here that these illusions are actually something that's very applicable to VR. I'm just using them to illustrate a point that what you're seeing and what it's really rendered might not be the same thing. This one definitely has a motion illusion there. You're perceiving motion even though there is no motion in the image. So perception, a lot of people are actually thinking about perception in VR. And if you guys have been here for the Mel Slater's talk earlier this morning, he's a good example of what typically people do with VR and perception, and that is they use VR as a tool to study perception, how we perceive things. The way that I think about perception is that I would like to think us a little bit differently. I would like us I would like to say that, insisting on as real as possible can leave you to design suboptimal AR VR experiences. And I would like to think about AR VR interfaces as perceptual illusions that give you the perception of reality. So in other words, I would like to use perception as a tool to create better AR VR experiences. I'll give you a few examples, and most of these examples are from my own personal work, so they span a lot of different categories of experiences, but I will try to illustrate these points through about 4 examples. So first one. This is the human field of vision, and as you can see, it spans kind of 180, 190 degrees horizontally and a little bit less vertically. But if you actually map that on the VR set, and this is kind of crudely mapped, you're currently dealing with about 110 degrees in there. And everybody's trying to create, of course, it's very important to create this wide field of view immersion, and people are trying to push that out. But one important thing that people are overlooking is that if you look at the human visual field, what we perceive in the periphery and what we perceive in the fovea area is not necessarily the same. As a matter of fact, in the fovea is where you get the detail, you get the textures, colors, all that kind of stuff. In the periphery, you're much more sensitive to motion, to contrast. You don't see colors that much. You don't see textures. You don't see detail. So one of the amazing pieces of work that most people don't know is that this just an addition of one white LED in the periphery. In other words, lighting your HMD inside. And this is a very small field of view HMD, 60 degrees HMD, has a drastic change in perception of how you perceive the space in VR. So typically, in this academic community, people know that people underreport distances in virtual reality with the reduced field of view. So if you have a 60-degree field of view, you're basically reporting distances somewhere down here, and if you have a 150-degree field of view, you're something like this. But if you do a 60-degree field of view plus one white LED in the periphery, your sense of distance, your sense of scale of that space approaches to something that has 150 degrees. That's amazing, right? Right now, everybody is focusing on pushing all the stuff in the periphery without really starting to understand what you really need in the periphery. So, as an example, an intern and I built a device that we call sparse peripheral display, which is basically a kind of an older style Rift device, the Rift DK2, plus 72 LEDs in the periphery. And what you can see here is this kind of idea. So the focus area, you end up completely focusing on existing imagery in there, and we render the periphery in a very sparse way. And there's a profound difference in how you feel this versus the tunnel vision of the stuff, and it's actually super trivial to implement in that case. But what's more interesting is that you can start using periphery not just as an extension of the field of view, but actually to help you out. So we published this particular design, which we called countervection stimulus. So many people, by expanding the field of view, many people experience increased simulator sickness feelings. So if you are targeting wide field of view devices, you will have more people experiencing sim sickness. And for us, we use the periphery to actually inject motion that counters the motion that you're experiencing, that gives you this feeling of sickness. And I'll show you how it looks. So there's this vertical stripes and horizontal stripes in there. So if you look around, this is the motion that you eject with the joystick, so it's not something that you vestibularly feeling. You can actually create these extra stimulus on the periphery that counter the experience. By all accounts right now, and we're actually running a little bit more formal study on this, but by all accounts right now, the people who are prone to experiencing simulator sickness have a very good success with this extra kind of help in the periphery. Now this is just one example. Let's talk about something slightly different. Today, when you talk about AR, VR, most people have an image like this in their head. They're thinking about headsets, they're thinking about immersion in a kind of a headset way. It's mostly kind of a solitary, I would still say solitary and personalized experience. few years back, we set out to think about what kind of augmentations of the space can you do if you're really considering the way that we consume media and entertainment right now, which is kind of the shared way in your space without having to wear things, without having to, with easily being shared, but still interactive. So this is a demo, and I'm just going to play it, of one of the pieces that we created to kind of highlight the opportunity there.
Xbox, go big.
So first of all, I want to say I wish all my research videos looked as good as this, but unfortunately they don't. This was shown at CES 2013. So there's a little bit higher production value in these than I usually put in to highlight some of these things for conferences. But we set out to kind of re-envision how would you apply augmented reality to the television experience. So we were driven by this idea that can the content of the television viewing, the content displayed on TV, can it spill out and engage your room in an interesting way? So the basic premise of this experience is the fact that you have a projector and a camera, and a depth camera in this case, that scans your room, understands the geometry of your furniture around it, and adapts the content for it, and finds a TV in there as well, so you can literally extend the field of view. So the first thing, of course, that we did when we created something like this is this particular experience, which is you're playing a shooter game, and you're literally extending the field of view on this. And while this is impressive, I would have to say, if all you want is a bigger picture, you should go to, Best Buy or your UK version of Best Buy and buy yourself a bigger TV, because it's going to be much better than anything that we can do. But when we started working with the Xbox game studios and game designers, it quickly became apparent that what we can do, that again, taking that same philosophy, what you can do in the periphery, if it's not the same as what you can do in the focus area, becomes a lot more interesting. So let me show you a simple example just to kind of illustrate the point. If you make, this was supposed to be playing, but maybe not. Hopefully the others will play. If you simply strip out the textures from the periphery and put an edge filter over the experience, in other words, you are accentuating the contrast and the edges. By a lot of metrics, people feel more immersed because they're actually receiving more motion. They're getting the important stuff that your periphery can perceive actually becomes highlighted, and it changes the nature of the experience, even though technically you're displaying exactly the same content. Let's hope that this one plays. Okay, it does. So this is another what we call illusion, which is the idea that you can be selective about what escapes the TV. Rather than selecting everything, in this case, only show explosions, maybe your enemies or bullets and things like that. So those end up being, even though you're really just selectively rendering what happens in and out, it ends up having a lot of elements of surprise because you don't expect certain things and you expect certain things to be out there. This is an interesting one as well, which is, since we know the geometry of the room, we can automatically make it appear like you're playing the game on the back wall, for example, segmenting your front furniture experience. And this now gives you this ability to basically do automated set dressing. So you can, if you're playing, let's say, a black and white movie, you can make sure that your room looks black and white. And if you're doing a cartoon, you can do cartoonish things. Again, this is just projecting directly on the furniture, so you're providing the light source, and you can complement it in interesting ways to do that. Here's an idea of tying just the experience. So experience is literally about driving in through the snow, and you can apply basically a snow shader onto your room. Now the snowflakes don't even match, but it doesn't really matter. It becomes really engaging. It becomes really interesting. As you drive through this game, more and more snow accumulates on your carpet, and as you walk through the carpet, you can leave footprints on there. Again, those subtle moments of not exactly following the content, but following the things that you would perceive correctly in the room actually end up being the lighter moments in the experience. This is one of the favorites for people, and it's the idea that you can reproject motion and have illusionary motion in the scene. So what we're doing is we're reprojecting the room onto itself, but by putting a disturbance in there, doing a radial warp, and as you're doing it, and that creates this illusionary motion of the room itself is shaking. Or this one, where we stole the lighting from the game, but that's about it. We relight the room based on the lighting in the game, and it gives you this visceral feel of driving, even though nothing else in the room is really driving. So hopefully this kind of illustrates the power that you have to create augmented reality experiences that are truly situated in the room, and B, the power of tailoring that experience in a perceptually salient way, rather than just following, like, let's extend the field of view all the way. So over the years, I've done a lot of projects that really push this idea of projector camera as a primary driver of augmented reality experiences. As you see here, there's lots of different projects that we've done over the years. The Illumiroom is the one on top that really kind of use this as the core technology to provide augmentation in space. But most of these have been used to basically in what I call surface shading mode, in the sense of like providing textures on existing surfaces. What we were really interested in is, can you actually create perspective views? And perceptual artists have been really effective in demonstrating this in a static way, right? If you assume a particular position in this space, you can really see this perspective, and it's amazing, but for everywhere else, it's not the case. I'll show you a few more examples because I think they're quite powerful on their own, especially because they're taking exactly from the perspective that they are. One of my favorites is this one in the garage in Australia, where it's actually used in a correct way. The perspective tells you whether you can read it if you're in the correct perspective, if you're going in or up or something like that. But if you're off perspective, such as kind of like this down here, when you're reading this, you can't read that this is going down. You can only read it when you're having a correct perspective in there. So we wanted to be able to recreate this particular experience, but truly for the room around us, and without necessarily having to make the people using this technology wear anything. So turns out you can definitely do this, and having a technology kind of like the depth camera actually helps you quite a lot, because the stuff that you need to solve to actually enable this kind of augmented reality is you need to understand where the user's viewpoint is. In other words, where they're looking from. You need to understand what's the room geometry, what is the surfaces that you have in the space, both how they look and what their actual geometry looks like in terms of vertices. And you can easily acquire that with a depth camera. Now, if you have that, you can now have a virtual object that you want to display somewhere in space, and you can figure out what the user should be seeing, and therefore what the projector should be projecting for the user to see that particular virtual object. So this will be easier explained if I just show you a video. So this is an early prototype in here, and the idea here is that you have, this is from my perspective, and in a second I'll go to offside, but you see this ball projected in my hand. Of course, if it's off axis, it doesn't look correct, but if it's on axis, it looks correct, and you can literally use the ball, and it even has physics, right, so you can drop it and play with it. Part of this projection actually happens to be on my hand, on my body itself, because this is done in real time. We're capturing 30 hertz of both depth mesh data and RGB data. And part of it is also projected in the background. Here's another example of it. We call this a beam-a-buggy or beamatron idea where we're literally projecting a virtual car driving over the scene in your living room, so you can drive it in any particular way that you would like. And we can also do this for two people. So this is a later system where where we noticed something, that if you're talking to somebody, most of the projections ends up being most of the projections that you end up seeing are projected either on your partner's body or their background. So in other words, places where they're not going to actually see anything. So if you have two people face to face, you can literally use this projection trick, view-dependent projection, to create objects, kind of hologram, the way that my company likes to call them right now, in between the two of you, and understand that. So I'll show you a little bit how that's done. So as I said, first you need to figure out what the user should be seeing. So this is a rendering, this is an off-screen rendering in memory of the computer, where everything that's gray is basically reality, and everything that's colored is something that I want to add to that reality. So that's a view from my head that a computer thinks that I should be doing. Then I feed that into a projector with a distortion map. So this is the distorted image that projector gets, that projects that image, and this is what a GoPro mounted on my head will see exactly in there. So this is a person in there, and part of this projection is on his body, and part of it is somewhere else. The same thing happens for the other person opposite there. Notice now we're looking at India, not anymore in North America, but again, the image in their head, the image the projector sees, and in there. So this is real-time live image of this system in action. So you can kind of see both of them are seeing an object projected right in their space, and not only that, they can actually interact with that object. So you can literally grab it, turn it, move it. And again, I want to remind you, this is augmented reality, but without the need to actually wear anything or have personalized views. You have personalized views through projection in many ways. This is a favorite one. People often ask us, well, how do you perceive these objects? There's no stereo. How do you perceive them as spatial? Do you understand what's actually going on? Well, the system is good enough that two people can play catch. You can throw a ball to another, and you can catch it on the other side. This is a unity view. This is kind of a side view of what's happening. The fact that you can actually catch a ball in midair is a pretty good indicator that you perceive something as a spatial object rather than as something that's projected behind you as a sticker on the wall. We've also done other experiments. We tested this with many different things. People are pretty good at interpreting spatial references. So if you point to something, I can understand what you're pointing at, even though these things are imagined to be projected between us, but are really projected behind me and behind you. So in other words, we do share the shared sense of spatiality of every object. So I'm going to do a little plug right now. I'm sorry about that, but we released this toolkit. So if you guys are interested in actually trying and experimenting with view-dependent projection mapping, we've released a toolkit that does several of the hard things and also binds it into the kind of Unity engine. So we provide you a calibration utility to calibrate multiple projectors and cameras, real-time depth streaming and rendering and shaders, all that good stuff, as well as all the Unity plugins to create experiences like that. I would, if you're interested, please check it out. It's all the code is available. Let's go on and let's talk about the next example here. And that one is, again, switching gears a little bit, but dealing with haptics. So most of the experiences right now that you experience in VR really lack any sort of tactile sensation. I believe it was Sarah a few talks before was talking about sense of smell in VR, and I was particularly interested in this lack of sense of touch, or lack of sense of haptics in VR. And not only that, I mean, there are solutions kind of like what I'm rendering here. There are solutions that are pretty kludgy, but that will give you a sense of what's happening. You have a little tactile feedback. They either require grounding, so in other words, the device is somewhere located in space and some force feedback is there, it's only one particular point, or they're pretty complicated to put on and take off, and again, very limited in the experience. But what really got us started thinking about rich haptics in VR is this particular experience. We put a Kinect and piped the Kinect data straight into a Oculus view. And then we had just a table filled with objects. These are real objects. And I have to say, this experience, even though it's banal in reality, in VR is fascinating. If you ever have a chance to do something like this, it's fascinating because anything that you touch is right there. Anything that you move, it's right there. You can juggle, you can feel the edge exactly where the edge feels, and it is amazing. Even though the rendering is crappy because of course it's just a kind of depth camera rendering. But so we set out with the idea of how do you actually do this? Can you create as rich of experience like this in VR? One of the first complaints that you hear when you give people this kind of Kinect demo is they say, well, passive haptics, which is kind of the scientific term for these experiences, having a one-to-one mapping onto the real object in VR, those approaches just don't scale. And that's a valid criticism. It's true. If you want to build a castle out of blocks, and you want to have passive haptics, you need to have kind of a one-to-one experience to each of these objects. So you need to have as many blocks as you want to do it, or you need to have a proxy object for everything that you're going to be touching in VR. Well, we started thinking about it down that path, and then we started realizing, well, that might be a fallacy. Really, VR gives you this amazing opportunity to literally fool people into thinking something else. And rather than me telling you this, I'm going to have Madi narrate this through the video because he spent a substantial amount of time making this video, so I think it's kind of fun to try it. He had some fun. I hope it plays. Oh, yeah.
Wouldn't it be nice to use real cubes to make a Minecraft castle? Well, the best thing you can do in VR is this, moving cubes around with a virtual wand. To have haptic feedback, you'll need a castle's worth of cubes. Luckily, we found a perception hack that makes you need way less. Like, really less. Like just one cube. First, you'll need a Kinect 2 mounted above your head, then a fully tracked HMD, mount a button pressing device to your desk, grab a trackable cube, strap a marker to your hand, and you're all set. For our first magic trick, we'll show you 3 physical cubes on a table. The moment you put on the HMD, we'll quickly grab 2, leaving only 1 behind. You'll see 3 virtual cubes, thinking they map to the same cubes you saw earlier. Then you'll be asked to reach and touch the cubes one at a time. As you reach for the cubes, you'll be wondering what the point of this demo is, but you won't know you're being fooled until you take off the HMD. Behind the scenes, we're using body warping. As you reach for the target, we warp your body space to provide the illusion that you are reaching for a different cube each time, when in fact every time you're touching the same single cube. In another illusion, we use a different mechanism to map a single cube to a ring of cubes around you. After inspecting each cube, you need to face a billboard to trigger activating the next cube. When you look back, the other cube will be ready. You can reach out and grab the cube, and surely the tactile sensation will be there. This time, we are using world warping. As you move your head around, the world ever so subtly rotates around you as well. This rotation is used to align the physical cube with the new virtual cube each time you look to the trigger board. Body and world warping can also be combined to form a hybrid approach. In our haptic retargeting framework, head motions trigger world warping, and hand motions enable body warping. We hypothesize that by splitting the job of aligning between both mechanisms, undesirable artifacts of each method can be mitigated.
So let's pause for a second here. I just want to reiterate, we are actively trying to fool you for a specific purpose, and the specific purpose here is to give you a better experience, better interaction in VR, give you haptics when you don't really have haptics. But but I want to just highlight the two techniques that we're using in the hybrid approach that that ended up using. The first one is called body warping, and that is that even though we are rendering how your hand looks like in VR, it's not exactly the right place. Everybody in VR is super obsessed with making sure that, you know, all the motion is one-to-one, all the tracking is one-to-one. Well, I'm telling you, it might be beneficial to not really do that. It might be beneficial to do this when you want to reach for something, we literally render your hand going somewhere else. Even though, you know, you're touching just for the purpose so that you basically meet up with the existing physical cube that you want to touch. The second one we call world warping, and it's also basically it's inspired by a known technique in VR that's used for large spaces, which is redirected walking, which is you can inject a little bit more or a little bit less rotation into your head view every time you rotate your head to get the world to align to where you'd like it to align. So if you do this aggressively, you will make people sick and throw up because moving world around you is bad idea in VR. But if you do this slightly when the people are actually moving, you don't perceive that as extra movement. And then that's another opportunity for you to fool it. So in hybrid approach, you're basically combining these two and doing as best as you can with either one to get you the interesting goal, which is kind of what I illustrated before. So let's just finish the video and then I'll talk a little bit more about it.
To put this to the test, we conducted a user study to gauge immersion levels associated with each approach. This minigame uses haptic retargeting to provide the illusion of arranging and stacking different cubes in the virtual environment. As the instruction billboard guides you, each time you place a cube in the correct location, with the press of a button, it will solidify. Then, a new cube will spawn to continue the rearrangement. Though it appears you're reaching for a new cube, you're actually moving the same one. Participants reported higher presence levels from the hybrid approach in comparison to each warp used individually, and overall preferred haptic retargeting over the virtual wand method. With spatial warping, in addition to spawning new cubes, we can also provide the illusion of stacking. This is done by applying a height warp as the cube is moved around. This close-up shows how the user feels haptic feedback from the table, convincing the user that the bottom virtual cube actually exists. With our system, haptics can be repurposed for a richer immersive experience, enhancing the user's sense of presence. So if you're tired of this, and you like to see more of this, you'll have to keep one thing in mind. If you want haptics, we've got the tactics.
All right. All right. So, as you can see, the student, actually another great student from USC, did a great job and a little bit carried away with the video. But I think it illustrates the point really well. I want to say a few more things and then I'm going to conclude. But one thing about this particular experience, especially things with stacking and things like that, is if you keep doing this, if you're, once you're putting these 9 cubes together, building this little castle, eventually you will notice that something is not quite right. We're not fooling you to such an extent that we can carry this on forever. But what's really interesting, and we showed this to a lot of people, and we took it to conferences, and people, at the conference floor get to try it and all that kind of good stuff. So literally hundreds, maybe even 1,000 people overall have seen it. What's interesting about this kind of experience is that even once you notice that you're being fooled, there is no incentive for you to try to effectively break the system. If you play along with the rules, you get a better experience. And people basically, even when they notice it, they're like, I know you're cheating, I know you're fooling me, but this is awesome. Let's just keep stacking, And I think that's a very good metric. This is exactly how we need to start thinking about some of these AR, VR experiences. If you're fool to the best extent that you can, don't disrupt them, but make it such that even when people understand that they're being fooled, they want to play along. So in conclusion, I hope in my talk that I've convinced you that insisting on as real as possible designs can lead to suboptimal AR/VR experiences. I also hope that you take away that human perception offers clues on how to effectively engage and more importantly, fool or trick the user. And lastly, I think designing interactions with perception in mind can lead to better experiences even when the user is aware that something is not quite right. So to get best AR VR, I think you should cheat as much as possible, but do it in a perceptually salient way. Thanks.
Okay, thank you, Benko. That's really, it's really interesting, these talks. What we're trying to do is maybe challenge you people to take on some of this stuff. And this is a good example, because I think this is a neat idea, trying to trick people and things. Have we got any questions? I'm sure Benko will be happy to answer some.
Hi, so great talk. I'm interested in hearing your perspective on some games and applications have used peripheral blinders, where they darken the scenery in order to minimize motion sickness.
Yep.
So
It's a really good approach. Again, it was also in the academic community. It was published a few years back, and it's a very effective way, especially if you do it very seamlessly. And so, in other words, when during motions you selectively dim the periphery, and then when you are stationary and all the motion corresponds exactly to your vestibular motion, in other words, you're turning around, your periphery expands. I have to say, I tried the experiences even just as demos, and it falls into this category of it's almost unnoticeable. It's barely noticeable when I'm doing it, because as you're moving, you have a lot of motion blur, you have other things that are happening, and you're not focused on this peripheral part about it. And so I think it's a very good point.
Yes, and I'm wondering, especially with you did some inverse motions in the peripheral vision. Yep. Is that possible to replicate with the headsets today, or?
Well, we didn't want to change the content on screen. So we injected this motion in this little sparse peripheral display, which is literally just, I think, 72 LEDs in the periphery. It's not that hard. We have a paper on this. You can find us on the website. Currently, there are no displays, there are no HMDs that sell with any kind of sparse notifications in the periphery. I think it's a good idea, because I think, for example, we did other tasks with that particular display in terms of, let's say, targeting. It's very easy to just highlight where you should be going, and you're kind of instantly doing your search for targets stops looking like, scanline searches. You actually directly go and target what you want to target, even with 4 LEDs in the 4 corners of the periphery. So there are very good uses for this beyond the stuff that I talked today, but I don't know of any commercial ones that are available, but you can easily build one yourself and try it out.
Yeah, thank you.
Yeah.
Any other questions? Guy at the top there.
Hey, thanks for the talk. So there's a lot of stuff in the academic community on incongruent perception. I was wondering, you spoke about scale, so how does this technique scale? So is it just in this small, very controlled context of moving blocks, or would this scale to multiple objects moving in the...
It's a great question. So in about a month's time, we will have a follow-up work on this, where we actually try to address some of that stuff. So the first thing we did is this one, the last one, haptic retargeting, was done with kind of pre-described targets. We tell you should be touching this one, now touch this one, to not touch this one. That's all fine, but for certain kind of experiences that works, for most of it doesn't. In the second iteration, we ended up using an eye tracker in there, and we are predicting what you're going to be doing. And we believe we have at least half a second, sometimes up to 2 seconds of time to warp. So a lot of times we can basically simulate a free choice scenario where you have a bunch of different objects, and we can retarget you to maybe 1 or 2 proxies that are right in front of you. Of course, as with all of these experiences, the scale is a big issue. I don't think it's going to scale to every experience ever, but for a lot of these things that are small, that are contained, that you don't move around too much, I think they're going to scale fine. I think I really look at them more as a set of techniques that, depending on the experience, you can employ or choose not to employ, rather than like a generic haptic solution for VR, period, right? So I think at redirected walking, I think of, in VR, there's lots of situations where you can have overlapping spaces, and they're completely fine perceptually. Like you walk out of the room, walk in there, and the rooms are both huge, but you don't perceive them as being one on top of the other. They're just side by side. All of those examples are just very good examples of perceptual knowledge that you can apply to your game or your scenario that might work for those particular parts.
Any other questions? No? Okay, can we thank Benko again? Thank you very much.
Cool,
Great.
thank you guys.